So regarding the homework, so basically addresses Hannah's wish to see the full calculation of the power spectra. But notice very important thing there is that you really have to address only section 7 and 8. So, you know, the whole thing is basically going through some details which I'm going to skip in the lecture. So I'm going to discuss this probably on Thursday and Friday. I won't have much time, but I'm going to spend some time, and probably I will go through section 7 and 8. So basically you have nothing to do, right? So the homework looks horrible. And if for those who are interested, you can go through all the steps, and you can consult Weinberg's book, chapters 5 and 10, where all these things are done in detail. But basically, it's for your own thing, just to see how the calculation goes. What I'm going to skip in the lecture, and I'm just giving the results basically. So it shouldn't take more than 2 hours, I think. Okay, so that's the homework. So last time we discussed a little bit more about this CMB power spectrum, and there should be a star here. Thank you so much. And so what we discuss is, you know, how these variations in temperature, which we observe in our CMB, and we expand them in these spherical harmonics, and it's about measuring these guys. So in some sense, you can construct this power spectrum, which is just the rotational invariant power spectrum constructed out of these A's. But the problem is that we have only one measurement, right? So the universe happens only once. You observe it only once. So we have only one measurement of these guys. So, and it may happen that, you know, the same underlying physics describes completely different ALMs, right? Because, you know, simply have a probability something happens here, something happens there. If I observe only once, I see only one measurement. And the question is, how do you do statistics on one measurement, basically? Okay, and so the idea is that you say, well, I have some underlying theory, and that theory gives me the probability distribution. And so basically the theory has to give me, whatever that theory is, how to calculate various correlation functions given, well, how to calculate various averages of various correlation functions. So what you assume about this distribution, which is consistent with observations, is that this distribution function is rotationally invariant, and it's Gaussian, which means I can, through the big theorem, reduce everything to 2-point functions. And then these coefficients CL describe everything there is to know about your probability here, about your probability distribution. So once I know CL, I can calculate 2-point functions, and I can reduce everything into 2-point functions, so I can calculate any average I want. So anyway, so this is good. So now I'm using the definition for the observed things, and I calculate. So I take these ALMs to be living in that ensemble, and I calculate the average of these CLs using this formula here. And if you do it, you find that the average is exactly those numbers there. That's why I call them CL. And then, however, there is this variance, which actually tells you that for small l, you don't see, you may have big fluctuations between the average and the observation. Very good. Questions to this? So this is all about temperature. However, CMB is very nice to us, and it doesn't only contain temperature, but photons contain also polarization. So let me briefly discuss a polarization. And so basically, as we discussed, you know, when the CMB was released and stuff like that, before photons completely decoupled from the plasma, we mentioned that there is this Thomson scattering. Okay, so Thomson scattering is good to us because it produces polarized light. So now each individual photon will come to you with certain polarization. So individual photon has polarization EI. Okay, so it's a vector, which of course is a unit vector. And so if you want to know how many photons with given polarization come to you, you need to describe that by this distribution function, similar to what we did in the thermal history of the universe. We used the distribution function, and that gave us the number of particles of a given species. But now this distribution function will have some indices. In order, if I contracted this given polarization, I get that number. Okay, so we have a distribution function. In this case, it is a two-tensor Fij, which depends on the position, moment, and time. So now we have that Ei delta Ij Ej equals to 1. That's a normalization of my polarization. You also know that when photons come to you, the polarization is perpendicular to the direction of propagation. So you know that delta Ij Ei Pj equals to 0. So P is the momentum of your photon. And so this distribution function is simply defined. It gives you the number of particles for a given so if I want a number of particles with given polarization, it's simply given by Fij Ei Ej and then your phase space integral. Okay, so that gives you the number of particles. So we are after this polarization function. And so, of course, what we observe is this Fij. Well, the position is on the Earth, right? So Q, and usually you put to the origin of coordinates. So Q equals to Earth equals to 0, Earth with vector equals to 0. So anyway, so we place ourselves in the origin of the coordinates. And the momentum is, of course, given by the energy of the photon, E equals to P, and it's coming towards you, so it's with minus n. So it's minus E n. So if I'm looking at the direction n, this is the momentum. The photon comes at me, and of course T is now. So this is what we observe. So this tensor is it's a symmetric tensor because I sandwich it with E's, they are the same, so it's symmetric. Only symmetric path plays the role. So it's symmetric tensor on the sky. Okay, so symmetric tensor on the sky. Okay, so far very easy, right? So now how to deal with symmetric tensors on the sky, or symmetric tensors in general, is through the SVT decomposition. So there is a mathematical theorem which is called SVT decomposition. Which is, in some sense, saying that any matrix can be decomposed into symmetric matrix and antisymmetric matrix and stuff like that. So this is an analog of that. So that we just stated for a symmetric one. So any symmetric tensor in the dimensions, can be decomposed as follows. So I have that tensor Tij. Okay, and then you decompose it into transverse traceless part, Hij Tt, plus a symmetrized product over a transverse vector, and then there's a scalar, two derivatives of the scalar, and then Gij plus square of phi, and then plus 1 over d psi Gij. Okay, it's a mathematical statement that any symmetric tensor, two tensor can be into these things. So what this T means is that, well, so this guy is 0. That means it's traceless. And also the transverse means that if I take a covariant derivative of that, the divergence of H is equal to 0. So nabla I H I J T T equals to 0. And the same for the vector. So nabla I Vi T equals to 0. So that's what that transverse means. Okay. So naively counting the degrees of freedom, so for example, Vj would have the number of components, but thinking about k-space, this represents one equation. So in fact, Vj has only d minus 1 non-trivial components, and so on. So try to calculate that. Really, it gives you the full rank of the full degrees of freedom of this tensor. So we have one scalar here, another scalar here, then we have a vector, and then we have a tensor, and so that's why it is called scalar vector tensor decomposition. Okay, so specifically, if you look at d equal to 2, so we want to decompose our distribution function on the sky, which is a distribution function living on the sphere, right? So we want d equal to 2. So we want the sphere, so d equal to 2. So then everything simplifies. So specifically for d equal to 2, so we are on the sphere. You can show that, well, Hij is equal to 0. And then its transverse vector is actually dual. So it has only one component. Now, so it would have two components, but because of the transverse condition, it has only one component. So it's actually dual to a scalar. Okay, so we can write Vit to be epsilon ij. This is my Levi-Civita tensor on a sphere, on a two-sphere, epsilon ij, dj, and chi. Okay, so on a sphere, vector has to looks like this, and Hij equals to 0. So if you look at that, we have only 3 scalars characterizing any. So we have 3 scalars, which are chi, phi, and psi. Okay. Yeah, sure. So now, if you think about what the psi gives you, so psi actually, is just a trace part, basically, of these things. It's proportional to Gij. And so that psi contains the information about the temperature. So it contains, it's a trace part, it's the same everywhere on the sky, sort of. It's like psi times delta Hij. So it's actually, that already contains that information about the temperature. So let's not consider this guy. So this one, describes temperature, which we already dealt with, right? So then we have to deal with the polarization, which are these 2 scalars here. So in other words, using the theorem, our, well, Tij or Fij is epsilon I k nabla j symmetrized nabla k chi, and then plus nabla I, nabla j, minus 1/2 gij, nabla square on phi. So that's the form any symmetric two-tensor on a sphere has to have.
David, can you explain again why the hij was?
Well, just counting number of components. So you have a 2x2 tensor, which in principle, it's a symmetric one. So in principle has, how many components? It has three components, right? So now you're imposing that the trace is equal to 0, which is one equation. And then you're imposing that the divergent of this thing is 0, which gives you two equations. So possibly it kills all three components. So that's why hij is.
I get why when we're going to re-study psi, but not why you can completely neglect it when you're writing that.
No, so what I'm saying is that, well, you can study it here, but basically what it will give you is, again, basically the discussion of the temperature, right? So you can keep it here. So, because we did it this way, you first discuss temperature, and now I'm making it more complicated. Of course, if you started just from this guy directly, you would discuss psi, and that would correspond to the temperature variations. Yeah. But let's start from something easy and go to something more difficult. Okay. So now, this thing allows you to construct something which is like generalized spherical harmonics, and so these are defined as follows. So, as are called tensorial spherical harmonics. So basically, you want to put one more index on your spherical harmonic, and you define it, for example, like this: epsilon ij lm, and then you will have two of them, one corresponding to this piece and the other one corresponding to that piece. So these are called E and B harmonics. Okay, so the E harmonic, so this is some prefactor, which is just some stupid prefactor, 2 times L minus 2 factorial L plus 2 factorial. And then, okay, so E is this one. Then you take nabla I, nabla j, minus 1/2 gij, nabla square, and you let that act on your normal harmonic. Okay, and the other one will be the same thing, B, Lm, the same prefactor, 2 times L minus 2 factorial, L plus 2 factorial. And then the other piece, which is, okay, 1/2. If I expand the symmetrized product, it's 1/2 this plus that. So that's 1/2 is there. And then epsilon j k nabla I nabla k plus epsilon I k nabla j nabla k on y lm. This thing. So that's a definition of two tensorial spherical harmonics. And it just, follow this decomposition here. And so having defined these, so by the way, they are orthogonal in the same sense as normal harmonics are. So for example, if I take an integral over the omega of ye, contracting all these I and j indices, I get delta L prime, delta M prime, and so on. So these things are orthogonal in the same way as normal spherical harmonics are. And so that means that, and they form a complete basis in some sense in this space of the two tensors, right? So they are orthogonal and they form a complete set for two tensors. So then I can write Fij as an expansion in this basis. So it's a sum over L and M, and then ALM now is index E, Y, IJ, LM, E, plus ALM, B, y I j L m b. Okay.
The sum starts from 2?
So L equal to 0 gives you
I think it starts from 2, right? From the gravitational wave expansion.
yeah, I would have to think about it. Maybe. Yeah. Okay. So I can expand this guy in my new orthogonal basis of symmetric 2 tensors. And so you see that now this thing defines new coefficients of expansion which we can measure on the sky. Right? So now we not only measure those ALMs, but we also measure ALME of one mode, of one polarization if you want, and ALMB of the other polarization. Okay, so there's much more information in the CMB than actually I claimed previously. So there are also these guys there. And then, similarly as we defined the theoretical CLs for the correlation functions between ALM and ALM star for the temperature, we can do these things for E's and B's. So for example, so define power spectra and now we have many more combinations. So the previous one, which I didn't put any E or B on those ALMs, sometimes people put T, denoting that you are talking about temperature. So for example, you may define, well, ALM T and AL star E LM prime. And this guy should give you delta LL prime delta M prime CL. And I will just put T and E, stressing that I'm talking about A's which belong to temperature and A's which belong to polarization E. And then I have CLEE and CLBB and CLBE and so on. So you have lots of power spectra, which you can in principle construct. Okay. So now the most interesting, at least recently, are the B modes. So B modes. So anything that contains these ALMBs. What you can, however, show is that not all these power spectra are actually non-trivial. Okay, so what you can show is that due to parity invariance, you have that CLTE equals to 0 and CL, TB equals to 0 and CLEB equals to 0. So whenever you have, only one B, then this is automatically equal to 0. Okay, so that's one thing. So basically the only thing which contains non-trivial B's is CLBB. Okay, so we have CLBB, which is ALM B ALM prime B equals to delta LL prime delta MM prime CL BB. Okay, so this is very interesting quantity. And so basically why this is interesting is that the source of these things, you have basically two main sources in the universe which can produce these B modes. So these are called B modes, and so there are only two sources. So leading sources, and so one of them is actually the gravity waves. Of the type which could have been produced during the inflation. So as your universe is rapidly expanding, so it's likely that the gravitational waves are excited, right? So if you have some violent thing going on, then it produces gravitational waves. So during the inflation, it's likely that you produce some gravitational waves. Okay. The other source is the secondary effect, which is a gravitational lensing. Okay. So second effect, which can produce these guys, excite these guys, is the gravitational lensing. Okay, so now if you plot how this CLBB should look like, if there were no gravitational waves, what do you observe? So it's CLBB, now I plot again L here. So now I'll just very roughly sketch that. It looks something like this. Okay, so this is mainly due to the gravitational lensing. So this would be true if there were no gravitational waves produced during inflation. So now if there are gravitational waves produced during the inflation, you see a small bump here. Okay, so this would be from the gravitational waves. Okay, so then you would see this spectrum like that. So now there was this big hello a few years ago when actually BICEP measured this bump. Right? BICEP. Actually, they measured exactly, these things here, and they claimed, okay, we discovered actually it was the first discovery of gravitational waves. These were the waves produced by inflation, and they just, because they measured this CLBB bump here. Okay, so the problem there, however, was that there is one more effect which can actually produce these CLBBs, and that is we are talking about polarization of photons which come to you, right? So this polarization is affected by polarized dust which appears in galaxy, and so what people did is that they measured how much polarized dust is in various directions, but they didn't measure how much polarized dust is exactly in the direction they were measuring these things. Okay, and it turned out that in that direction you have lots of polarized dust. So gravitational waves. So however, BICEP underestimated effect of polarized dust. Which can cause that bump as well. So actually that was, so that measurement basically went away after it appeared and lasted for about 3 years. But when these things were, put together with the Planck results, then we didn't see gravitational waves here. But these B modes, in principle, can be, a great source to discover gravitational waves in this BB spectrum. Do you have questions?
BB things does the variance blow up at small L as well?
It's a good question.
If the pump
I would say yes. I never thought about it. I would say yes naively, but so this was something that they claimed it's well beyond any cosmic variance or whatever. So I think they really thought that this is there, but the problem is that you can have plasma in the universe which still affects and can polarize your photons coming to you. Okay, but it's a good question. Find out and tell us next time. Okay, so this was very exciting, but it went away, and so we had the detection of true gravitational waves last week. Okay, so now that's all I wanted to say about CMB at this point. Let's return back to inflation, but let's understand it as a new thing. Let's understand it as a generator of fluctuations, of perturbations. So part B is inflation generator perturbations. And today I will just tell you the bedtime story, and then you'll start the calculation tomorrow. But of course, you can start working on your homework if you want to. Okay, so let's start. We'll do it in several steps, and never completing the last step. So let's start with a toy model. And so what I'll be doing is a test massless scalar field. In FRW, and then because the observations point towards the fact that basically we have like flat universe, but anyway the curvature in early times doesn't matter usually, then we will take k equal to 0. Okay, so then we have the action, which is d4 of x square root of g minus 1/2 g mu nu d mu phi d nu phi. So basically what we discussed before, but now, so you take, as before, g mu nu to be that of FRW, but you will not say that phi has to respect the symmetries of FRW. You will consider the spatial fluctuations of this scalar field. Okay, so in FRW, as we did before, you get this is equal to dt d3x. Now, square root of g is a cube, 1/2 a cube. So you are using the form of FRW where it's minus dt square plus a square gij dxi dxj, but gij takes just delta ij. Okay, so I'm taking here ds square minus dt square plus a square delta ij dxi dxj. So that's the metric I'm actually writing it. Okay, so it's 1/2 a cube coming from the determinant, and then phi dot square minus 1 over a square nabla phi square coming from the inverse metric, g mu nu. Okay, and so then your equation of motion is again what we almost had, but now we want the fluctuations as well. So it's phi double dot plus 3h phi dot minus 1 over a square. This is your equation of motion. And this guy talks about fluctuations. Okay. Test massless scalar field in FRW behaves like this. So next thing what you do is that you say, well, this is just a nabla on flat space. Is that you say, well, I do it in the Fourier space, right? So you introduce phi, k, and t, which is the Fourier transformation of your phi, but only on x. Okay, that's your flat space. You can do just a normal Fourier transformation, and your equation becomes phi double dot plus 3h phi dot plus omega square phi equals to 0, where your omega square is k over a. That will not work. Omega is k over a. Okay. So far, so easy. It's just really including this additional term to what we had before. So now, again, in some sense, this is something like having a harmonic oscillator is friction, right? So if this guy, is big, then we have big friction, and if this guy is small, we have small friction, and we have basically harmonic oscillator. So again, we have underdamped harmonic oscillator if this h is much smaller than omega. So h is much smaller than k over a. And if that is true, well, I can neglect the middle term, and I have something like harmonic oscillations, right? So oscillates with frequency omega. Okay. The other regime is overdamped. And that's the other regime. H is much bigger than k over a. And if that happens, then basically the oscillations stop, and the oscillator is frozen at that given position, right? So say mode is frozen. Okay. So now if you are looking at these things, why not to multiply these equations by a? Okay. If I put this a on this left-hand side, of course a is bigger than 0, then this is still true. So now do you recognize what HA is?
1 over r.
Aha, very good. So you'll say that the quantity HA is again a comoving horizon. So if we had comoving horizon radius, it was 1 over HA, and that had units of the radius. So now HA is 1 over that. So it is like comoving horizon wavelength, or comoving horizon. Let's call it K space analog of R hat. Okay, so we'll call that this quantity HA is also a comoving horizon, but now it has the units of wavelengths or whatever of K. So it's a K space analog of R hat. Okay, so now it's obvious that our conditions are that this comoving horizon is much more than K. If that is true, then we have a mode which oscillates with omega. And if the comoving horizon is much bigger than K, then the mode is frozen. Okay. So K is much bigger than HA. We have the oscillations, but there's a terminology used in cosmology is then you say, well, if K is much bigger than HA, then the horizon, that mode is inside the horizon, people say. Mode is inside the horizon. And if K is much more than HA, then we know that it's frozen outside the horizon. Just the terminology cosmologists sometimes use. Okay, so we have these two regimes of the behavior depending on whether K is small or bigger than HA. Okay, so of course, because it's frozen, you can sort of say that the mode is like conserved. If it is outside the horizon, nothing is happening to that mode. The mode is simply sitting there, waiting until the horizon actually does something so that the mode unfreezes. Okay, so that's very, very important. So let me now distinguish two cases of the behavior of the scalar field. So two cases. So case one will be like a normal universe, so non-inflationary inverse. So you know that you have no inflation when a double dot is smaller than 0. In other words, t over dt of HA is smaller than 0. So my co-moving horizon is actually decreasing. Okay, so then in this case, you can think about I have, well, scale of the order of k. So this is my HA, it's decreasing. Okay, and then if I have some k, so this is my k, then here I'll be outside of the horizon until here. Here I will be inside. But of course, if I have the scale field, then if it's outside, then it's frozen. It means that it has the constant value here, scale field. And if it's inside, it starts oscillating. So this is the behavior of the scalar field you sort of expect, just based on this very rough estimate. Okay. So now let's do this more precisely. So let's consider a radiation-dominated era. So for example, e.g. radiation-dominated era. Okay, so if you have radiation-dominated era, we derived long time ago that A is proportional to T to 1/2. So now H is A dot over A, which goes like 1 over T. It goes like 1 over T. And HA goes like T to minus 1/2. Okay, so what I draw here, that HA behaves like this, for radiation-dominated era actually goes like T to minus 1/2. So you have this picture, again the same picture, but just a little bit more thing. So now you know that in radiation-dominated, this thing which is HA goes like T to minus 1/2. And then let's say I have, so this is my T, and then I have TCMB somewhere here. And let's say here I have my plasma oscillates here through that fact. So for any given K, it's frozen outside, and then it oscillates. And then this one is frozen and oscillates. And this one is frozen and starts oscillating. So now basically if you can solve how this oscillation, how this thing propagates through my plasma, these oscillations. So I have an initial condition given by the value of the mode, given which is frozen here inside the horizon, outside the horizon. And then I have to solve how it propagates with this initial value to my time when CMB was released. And if I observe a maximum here, then it corresponds for a given L, it corresponds to a maximum in CMB. If it's a minimum, it corresponds to minimum of CMB for a given L. So these things, this guy is high L mode in CMB, and this guy is a low L mode in CMB. Well, L behaves like K, so I have large K, I have a large L as well, right? So basically, you know, if the picture is that at the time when CMB was released, I had a maximum here for that given L, then I have I see maximum in my power spectrum. In some sense, if I have a minimum, I see a minimum there. So this is how this is related to your CL as we plot it here. Okay, And so what is describing here, so this thing is, describes plasma oscillations. Plasma oscillations.
David,
Yes.
how is K related to L?
Oh, it's a complicated thing, right? But in some sense, it is related, right? So K describes a wavelength. L is your spherical harmonic L, right? So L is related to distances, but projected on the sphere. K is related to distances, but not projected on the sphere, right? So you have to relate these two through the projection on the sphere in some sense. but that's it what it is. Okay. Okay, so this is the normal picture, after the inflation ended and our radiation dominated era started, but I also have the picture what happened during the inflation. So in inflation universe, that's the case too. You now know that d over dt of HA is bigger than 0. So your picture is now opposite. So you have something like this. This is your HA horizon. This is your K. So now the phi actually will oscillate here, and then it's frozen here. So this is phi, this is time, this is time. Okay. So that's the behavior of phi, just by exactly opposite. Okay. So now I want to give you this general picture of what people think actually happened. And so let me draw a monstrous picture. And as I'm saying, it's like a bedtime story. It's not really that I'm going to explain all the details, and I think nobody can. But it's something what people believe sort of happened. So, a big picture. And it's really a picture. So I'll have a K here, and then I'll have time. Okay. So now, what we established is that during inflation, the horizon HA is actually getting bigger. After that, it's getting smaller. So let me sketch how this could have looked like. Something like this. Okay, so that's your HA moving horizon. Okay, so now you split this thing into various eras. So here, up to here, you have inflation. So before something, before inflation, something might have happened, but this era is inflation era. Inflation. Okay. Then this era here is the end of inflation, where you sort of have to, stop the expansion and transfer the energy to standard model particles and start normal hot Big Bang. So that's reheating era. And people don't know what's happening during that era. And then, here you have the plasma oscillations and so on. Plasma oscillations. So now let's say that this is my CMB time, and this is now. And you have happy observer here, looking through this thing. Okay. So now the idea is that during inflation, which was driven by the scalar field in the simplest possible case, the scalar field could have had these small spatial fluctuations. So these fluctuations are quantum mechanical fluctuations. Okay, and so they are naturally produced. So you would have like fluctuation coming here. So these are called adiabatic modes. I will not tell you why adiabatic, but you will learn in explorations. Adiabatic modes. And you assume that these are generated quantum mechanically. So, okay. So, somewhere during the inflation, the quantum fluctuations of the field, created quantum mechanical quantum fluctuations. Okay. So now, towards the end of inflation, you can show that despite that this is a scalar field which is quantum mechanical one, you can show that the commutator of the field and the momentum of the field is approximately equal to 0. You can show that. So what happens is that if you wait very long time, well, okay, take it back. No, here. So what I'm trying to say is that these fluctuations are classical. Okay, so during the inflation, the quantum mechanical fluctuations became classical fluctuations. The reason is very simple. So you have very, very small quantum fluctuation. Now you expand your universe like crazy. If you expand your universe like crazy, you stretch your fluctuation. So now your fluctuation is much, much bigger, and it cannot be quantum mechanical anymore in some sense. Okay, so that's the idea, what's happening. So here you have quantum mechanical fluctuations of the field. They become sort of classical at the end of inflation because your universe expanded so much that these things actually are classical. Okay. So now this time when the mode sort of crosses the horizon, it's called horizon exit. Horizon exit. So then we established that if you are over here, if k is much smaller than HA, then you are frozen. So these modes sort of wait for you here, and they don't change. They are frozen until they reemerge over here on the other side. Okay, so this is called horizon reentry. And so the guys here have conserved value. And people think this is amazing because, no matter what the equation of state was of the universe at the time of reheating, no matter what happened, how this HA looks like, there is a theorem called Weinberg's theorem showing that really these modes survive, no matter what equation of state was here. They just carry their value until they refreeze over here. Okay. So then, so you have these fluctuations in the scalar field, but of course these fluctuations in the scalar field, they induce fluctuations in your plasma, in your photons and then electrons and then plasma. And so these things actually propagate now to the time when this was released. Okay. So these are fluctuations not of scalar field, but of plasma. So all these fluctuations of scalar field have been transferred to the fluctuations of plasma. Okay, so these are plasma oscillations over here. And in order to get this thing here, actually, you need to solve these complicated equations, kinetic equations of what's happening with electrons, what's happening with photons, and so on during this time period. But provided the initial condition here set by the inflation. So the inflation sets you, produces natural fluctuations. These fluctuations survive, and they give you initial conditions for the motion of the plasma later on. That's the story. That's the bedtime story. Okay, so here, in order to solve how this propagates over here, you actually need to solve Boltzmann equation describing fluctuations of the plasma oscillations. But the important point is that really the inflation gives you the initial conditions here. Okay, and these are very nice and smooth initial conditions. Okay, so then the CMB is released over here, and so then you need a mechanism how to transform these fluctuations to fluctuations in temperature, the fluctuations in polarization, and so on. And so basically what you have to do is that you have to do delta T, and then you transform to CL. And then you observe CL. Okay. So really the whole point about inflation is that it gives you nice initial conditions over here. So inflation gives nice initial conditions So now, of course, you have fluctuations in your plasma, but so they go to fluctuations in CMB, but of course the other fluctuations may cause your structure growth, right? So if you have fluctuations in densities, then you may have gravitational collapse of your fluctuation, and you can start forming galaxies and stuff like that. So the idea is that this picture gave rise to all structure formation and all we see in the universe. Okay, so nice initial conditions, and that can actually give rise to large-scale structure. As we know it. And so in some sense, what we will do in the rest of the course is I'll try to calculate is what kind of initial conditions you get here. So why I do that? Because this you can sort of do analytically. Here, you really need to solve the Boltzmann equation for your complicated plasma to transfer it from here to there. Okay? And then you need to project it on the sky and so on. But what I'll do for the rest is really I'll show you that this gives something which is almost a scale invariant spectrum. So scale invariant spectrum is that basically doesn't matter on which scale the mode looks the same. And so this is precisely what inflation sort of gives you, right? So it gives you sort of a scale invariant spectrum. That gives you nice initial conditions here. If you have these nice initial conditions here, you observe CL. So there are Boltzmann codes which you can do it online yourself. So you say, well, this is my initial conditions. What do I get here? Okay, and so they will solve it for you. Okay, so what we will do is this part over here. So now I think we are extremely lucky that we have this Weinberg's theorem that says no matter what happens during the reheating, this mode is conserved. Moreover, what you assume that the reheating doesn't produce any more fluctuations. Okay, so you say, whatever the fluctuations I have are the fluctuations which were quantum mechanically generated here, and that's it. So that's the bedtime story. Questions?
Okay, what about the fluctuations of the matter fields that you have during inflation?
Sorry?
We have other fields around during that time as well. What about their fluctuations? Why don't they account for structural formation? Why do we need the inflation?
No. So, okay. So what you can show is that, well, this is much more complicated. So So for example, here the Weinberg's theorem tells you there is always one mode which actually is frozen and survives these things. So there may be other modes which are not frozen, and they can mess things up or whatever. But you just don't care about those modes. So they may be various modes. But what is interesting is that these initial conditions which you get are valid for all the fields. So no matter which kind of field you have, if you have electromagnetic field, if you have scalar field, gravitational, whatever. So they produce the same initial conditions. So all the fields are actually set up by the same initial conditions. It's something which you get from inflation. This wouldn't be true if you had, I don't know, cosmic strings or whatever. If you had some other theory, then actually your conditions which you would get, which would emerge here, will give you something completely different. And then you wouldn't be able to get actually the CL as you see it now. So in some sense, this is like an indirect proof of inflation, if you want. It gives you the right type of initial conditions. But all this is actually cheating, because in order to get these nice initial conditions, you'll have to impose initial conditions for these quantum fluctuations here. Okay, they are very initial conditions. You'll discuss that on Thursday, probably. Nevertheless, you still have to impose some kind of initial conditions here. People play with these initial conditions here. And so all inflation basically sort of does is tells you, well, I can postpone the choice of my initial conditions from here to here, right? So that's what inflation does for you, in some sense. But it's it's not that bad, because the initial conditions which you place here are quite natural, but people play with various initial conditions over here, and they get it's an active research. What happens if I impose different initial conditions over here, but I still get nice things here, and you can do that. Okay, so that's the picture. Let's finish here. Let's do the calculations tomorrow.